This is me trying to figure something out underwater. And those are NASA astronauts, also trying to figure something out underwater.
Copy, V1 taking you from point at 25 to gauge. That's room with the red box. What's that, the red box?
NASA is about to make a technical decision, and I want to try to explain why it's so important. Like, if you could design an entire moon program, you're going to take people to the moon, like they did with Apollo back in the day. However you take people to the moon, you're going to have to use a spacecraft, and inside that spacecraft, they're breathing oxygen so their bodies can stay alive. They'll then descend somehow to the surface of the moon, they'll touch down, and then they'll get out and walk on the surface of the moon in a spacesuit, which also has oxygen in it. For the Apollo program, there was the A7L suit with a plis on the back, the portable life support system. This device pressurized the spacesuit so that the human inside the spacesuit could breathe. One thing we don't think about very often is going from the spacecraft to the spacesuit. That step is critical, and it plays into this big decision that NASA has to make for the architecture of Artemis. The Apollo program was incredible. It put flags and footprints from humans on the moon, which is one of the biggest deals ever. Ultimately, though, the Apollo program ended. The Artemis program is going back to stay. People are going to live on the moon. This video is crazy town. The fact that we got to do this is amazing. So what we're going to do today is we're going to go observe a government test on a spacesuit, and then we're going to use that information to understand this big decision that NASA has to make. And the people we meet along the way are just incredible. Engineers, divers, astronauts, test conductors, all these people have a role to play in this big decision that will affect the architecture of the Artemis program. And I know the video's long, got it, whatever. It's worth it. I learned so much that I have to share with you, and I want you to go on this journey with me. I thought I understood the physics of being on the surface of the moon in a spacesuit. I didn't. We're gonna learn so much in this video. I'm gonna show you footage I've kept for years, I haven't shared. There's so many cool things in this video. I'm excited to share it with you. So let's go get smarter every day, and let's start off at the Neutral Buoyancy Laboratory at Johnson Space Center in Houston, Texas. In order to do this test, we're going to Houston, Texas, to the Sonny Carter Training Facility, NASA's famous Neutral Buoyancy Laboratory. Tim, the guy that made all this happen, met me at the door and escorted me in the facility, where he introduced me to two very important people. The first person was Dominic Del Rosso. Dom has done everything. He used to run the zero gravity program that I got to participate in as an undergraduate, where he did all kinds of research in early suit development and tools. He served as a fire chief. He's a backseater for NASA's WB-57 Canberra. Yeah, how cool is that? He's volunteered in Afghanistan. He's served as a test subject for NASA countless times. He's currently the chief engineer at the Neutral Buoyancy Lab because he's a diving instructor trainer, and he also serves on the dive safety board. Yeah, Dom's the real deal. The second person they introduced me to was Pat Keller. Pat is an incredibly experienced master scuba diver trainer that's trained thousands of people how to scuba dive. In his off time, Pat is a safety jumper for some of those speedboats that you see. He's the guy that goes in and saves the pilot of the boat if they have a problem. These guys are incredible, and they're about to school me up so that we can learn what we need to know in order to even get in the pool with the astronauts. Okay, we're here at the Neutral Buoyancy Lab, and this is Pat. Are you guys that's going to keep me alive?
Yeah.
That's the goal. Are you
goal.
Are you the instructor diver?
Yeah, I want to be an instructor. What I do here is I run the maintenance department, and I also run the scuba instructors here. So those are my two main jobs here. I also safety dive, float dive, but that's my main job. So when we get something like this, yeah, you're the one you're stuck with.
Okay, so I'm your problem basically for 2 days.
Well, that's debatable. I'm probably your problem.
Okay, that makes sense. And this is Dom. Dom, you are the engineering manager, is that right?
My title, I'm chief engineer here at the facility, but I wear a couple of different hats. I'm representing management here today as well. I'm also instructor trainer for diving and sit on our dive safety board. So I support Pat in what he has to do as well. So I'm going to be talking a couple different things, different areas.
You're making sure I'm staying at coloring in the lines kind of thing?
Yeah, well, I'm the government guy, so anything bad happens, I have to do the paperwork. So everything's going to go really well.
So Dom and I met each other a long time ago. I did the undergraduate reduced gravity student flight opportunities program when I was, that was like 20 years ago, and you ran the thing.
I really enjoyed that period of my career.
Okay, so the Neutral Buoyancy Lab, real quick, really big swimming pool. It's amazing. You can do specific simulations that you can't do anywhere else in the world. There's some facilities like it. I think in Cologne, Germany, they have a very, very small pool, but it's nothing like the NBL. This is a unique facility that the government has, right?
For our facility, it is for our space program. There's one in Star City in Moscow. There's one JAXA has in Japan. But by far and away, this is the most utilized and heaviest used one.
So. Okay, and so you guys use, I'm gonna look at this picture on the wall over here. You guys use divers, and well, I guess you are the diver.
One of them.
And so you guys can simulate zero gravity or other environments by attaching weights and getting like trim out buoyancy wise and all that good stuff.
Yep, we want you neutrally buoyant. We don't want you to sink, we don't want you to float, and no preferred orientation. And that way, this is the only place you can do all 3 degrees of freedom and do that. You still have weight inside that suit, but you can do the entire space station end-to-end 6-hour run with you and your buddy out there. So yeah, it's a pretty unique environment in the water. And I think we're going to talk about probably later about how now we're going to use it for lunar training.
Right.
So now I got to get you on the bottom at
okay.
16G. Okay. And then we also do stuff on the surface because we have to recover capsules. And that's our team here that trains our Navy and Air Force PJs to go out and help.
Air Force PJs, the
pararescue.
Oh, they're the people everybody, they're like, these guys are awesome.
So the Navy divers and Air Force pararescuemen do the nominal recovery of the crew, but our people here train them.
Okay.
So we do that on the surface as well as we also do aircraft water survival for our aviators and astronauts. So we do stuff on the water, under the water, on the bottom, all over. Daylight conditions at night, put your night vision goggles on, depends on the environment. So yep, when you're outside space station, every 45 minutes, you're gonna go from light to dark for a 90-minute orbit.
Right.
So it's gonna be full on bright for 45 minutes, full on dark for 45, and you're out there for 6 hours. So we turn the lights on and off, same thing here, and only your headlights.
So you mess with the photopic and scotopic vision in the astronauts?
Yeah, and it's not, again, and we're probably going to talk about this a little bit later, each environment is valid in some aspects and not others. We have water drag. So we don't do stuff that is high drag in there. It's not realistic, it's negative. You're going to get the wrong answer. It's invalid, right? So you put all these different environments together to get the picture. For here, it's that end-to-end working together 3D kind of thing. It's not really, as you get back to your vision stuff, we're not doing lighting, testing, evaluation like that, but we're giving them the operational sense.
Yeah.
Same thing we'll talk about lunar later. It's not doing soil studies here, it's underwater, I can't. But I do need to give you the same physical reaction and environment so you know how to operate when you do the other stuff.
You're putting their brain in the space, and you're having to manipulate your arms and stuff. Okay, so I'm talking too much. Okay. So what are we about to do?
Okay, so what we're going to do is we want you to get in the water with the crew tomorrow to be able to see what they're doing up close and really get a sense of the scale and everything else. To do that, we need to qualify you as a diver, but what we're going to do, since this is a one-off, we're going to have Pat here as an instructor do an escorted dive for you. So your current recreational certifications with an escorted diver in our working environment, what we're going to give you here is the difference between what we do here and a recreational dive, so you can dive here safely, get in and do your job. So we're going to get through this so you can get onto what you need to do.
As we move towards this big decision that NASA has to make, we have to understand some of the prerequisite information, and coincidentally, a lot of the physics has to do with scuba diving. This gets complicated, so obviously we should use a flannel graph. So the air we generally breathe is made up of several gases. You got about 78% nitrogen, 21% oxygen, with a tiny bit of argon, CO2, and some trace gases. When you dive in a swimming pool, the further down you go, the higher the water pressure becomes, and that has some implications. When the scuba diver breathes air from the tank, that air has to be compressed to the pressure of the depth that the diver is at. That means that the deeper you go, the more nitrogen enters your bloodstream. It's like absorbed in your body, in your blood, blood, nerves, cells, basically all your tissues. If you then return to the surface, all that nitrogen has to work its way back out of your body, so it tries to get out of your tissues. Now, you've heard of this. It's called the bends. You've heard of divers getting the bends if they surface too quickly, right? So divers are always working to stay on the correct side of the math so that they don't stay down too long and get too much nitrogen in their blood, and they don't ascend to the surface too quickly so that that nitrogen tries to rupture out of their body really quickly, causing the bends. Scuba divers are always thinking about how much bottom time they have. If I go down, the nitrogen will get in my blood, and then I have to be very slow on my way up. In fact, I have to do what's called a safety stop. I'll come up to a certain depth and let that nitrogen work its way out of my body. I'm going to watch the time, make sure that nitrogen gets to dissipate out. It's a very important part of scuba diving. People that dive all the time, they have this cheat code that lets them stay down longer. They have more bottom time. It's called EAN, or enriched air nitrox. And this basically is air, but they played with the percentages of oxygen versus nitrogen. You'll hear of nitrox 32, nitrox 36. That's 32% oxygen or 36% oxygen instead of the normal 21% oxygen. It's a really interesting way to offset the nitrogen buildup in your blood. Now, at the NBL, they go even farther. They don't use normal nitrox that a professional diver would use. They use nitrox that's got even more oxygen in it. And the reason they do this is because the NBL is a pool that's only 40 foot deep, right? So they've done all the math ahead of time, and they realize if we have this special nitrox that we dive in here with the pool, people can have all the bottom time they want, and then they can come back up at any time, and they don't have to worry about the bends. Long story short, the people at the Neutral Buoyancy Lab, extremely smart. They developed this special nitrox blend so that people can dive for an extremely long period of time and come up safely, and they never have to worry about decompression sickness on the way out of the pool. It's fascinating. My understanding is we dive with nitrox here, but it's a special kind of nitrox?
It is. It is. It's a much higher mix than you can get out recreationally or industrially because it's set up for the profile. So that astronaut in that pressurized suit that right now is about 4 psi over ambient. So at the bottom, it's going to be the bottom pressure plus 4 in for 6 hours. Well, I would be in decompression cycle at that point. If I was on an air dive for 6 hours at 48 feet equivalent, I'd be in decompression.
Yeah.
I can't do it. So I want higher oxygen, less nitrogen.
Yeah.
But if I get too much oxygen, it becomes toxic.
Yeah.
So I can't, like on orbit, the real one is an oxygen rebreather. There's no nitrogen in the system for the on-orbit suit. But I can't do that in the water because you'll be toxic. So we have this blend of 46%. So it splits that difference there, so we can do that safely.
My brain was on fire. Clearly, Dom has a lot of experience and he knows a lot of things, but I finally gained enough self-discipline to quit asking questions so that we could move on to the dive preparation part of the meeting.
See, each subject has 4 divers on them. They have 2 safeties, 1 utility, and 1 float. So you have 8 divers, 2 subjects in the water.
Okay. 8 divers, 2 subjects in the water. Is it 4 people per
subject?
Are those divers up on comms, audible comms?
Now, as you do, we hear them in the water because we have speakers. You'll hear this tomorrow. It's really cool. We hear everything the subject's saying and everything the TC and the TD are saying in the water.
Wow.
They can't hear us. It's a one-way. But we hear everything that's going on. So they can make requests to us. They can talk to us. We can hear things so we can prepare what we're going to do next. So yeah, you'll hear that. It's very clear. And it's one of the rules we have about speakers. You can stay about 3 feet away from them because they are very loud.
Okay.
All right. But you can hear them as if I'm talking to you right now.
Wow. As Pat went through the classroom instruction, it became clear to me that this is not a normal dive. These people are doing amazing things. There's nuances to what they do. For example, there's increased percentages of oxygen involved, so the fire hazards are different. They use a specific tank rig. The hand signals are different. All this stuff made it very clear to me that I'm not just dealing with professionals. I'm dealing with people who have been hand selected because of their unique temperament and their skills and their ability to react under pressure. The people that dive at the NBL, they're amazing. So it's time to talk about spacesuits. Now, when it comes to spacesuits, I have a unique insight into what it feels like to be inside a spacesuit because 9 years ago, I actually got to wear a NASA spacesuit. Now, it feels strange releasing this footage now because I did it 9 years ago, and at the time, I was an aspirational young man that wanted to apply to be an astronaut, and that's what I was doing. And so it didn't feel right to release this this footage back then, but I'm going to release it now because it helps illustrate a point. I know what it feels like to be in the suit, and I want to talk about it a little bit. Just for the record, I want to let you know what I feel about this footage. It's odd looking at it because it reminds me of like what could have been, but I keep my astronaut rejection letters right there in the shot of every Smarter Everyday video. I've got them all stacked up in this little frame. It reminds me that NASA made the right call. The people that are astronauts right now are absolutely incredible. So I feel weird looking at this footage because it feels almost selfish. Like, man, I really wanted to do that, but that wasn't God's plan for me. And I have comfort knowing that God had a different plan for my life. And we get to talk about spacesuits right now together because of this. Now, if you think about it, the spacesuits currently worn by astronauts on the International Space Station, they're not made for walking because the astronauts move around by grabbing handholds and moving with their arms, right? Well, the spacesuits that's about to be used on the moon, they do require boots that are made for walking, right? The suit I got to try on years ago was the older style, and I learned things by trying this on. First of all, I had to wear an undergarment. Now, if you think about a spacesuit as a self-contained spaceship, you have heat that your body is generating, and that has to go somewhere. On Earth, the heat dissipates through the air, but in space, it can't do that. So you have to wear this suit full of tubes that will dissipate the heat from your body by actually contacting your body and pulling the heat away. It's fascinating. Keep in mind, this is the older suit I'm putting on, and so getting into the hard upper torso from the bottom was very difficult.
Then you just got to kind of worm your way up. There you go.
Elbows don't do that.
Go ahead and look. Yeah. There you go. You got to try to come straight up, Destin. There you go. There you go. And it's a boy.
It's a boy. Also, as you put the suit on and they put the helmet on, it was quite the moment, by the way. The first thing you realize when they pressurize the suit is that it feels like a balloon. My hand was inside a glove, and the glove, as it pressurized, had a state that it wanted to be in. Like at rest, the fingers wanted to be in a certain position. As I closed my hand, I could feel my fingers having to work against the suit to close the hand because it was like being on the inside of a balloon, if you can imagine what that feels like. So what that means is the higher the pressure in the suit, the harder it would be to close your fingers. It's a fascinating feeling, and it was also very heavy. I found that the suit was very difficult to walk in, and I was kind of scared that I was going to fall forward or fall backwards. It was an interesting experience, and I'm grateful to have had that opportunity because it helped me understand the things that Dominic was about to teach me. So the change in pressure between what's inside the suit and what's outside, that determines how stiff the balloon is. What is a normal suit? So
the current space station suit, which is a derivation of the shuttle suit, is 4.3 psi delta over whatever it is. If it's in a vacuum, it's 4.3 absolute. If it's here, it's going to be whatever pressure you're at in the water plus 4.3. So it's going to feel and act the same way.
Okay.
And these suits that we'll show you, we'll review later, these are all downgraded flight hardware, and they're sized for you.
Oh, okay.
So it is exactly what you would be using. It is exactly the same delta pressure. Like I said, our environment here, the biggest thing is water drag.
Yeah.
And so we don't do stuff where drag is in the equation because
Okay.
it's not valid.
I see.
The other stuff is.
So are you going to do a higher pressure run tomorrow? That's my
Yes.
understanding that's what the
Yes.
test is?
Tomorrow's a higher pressure run, so the crew members can evaluate, and we're going to do it in the blind. We're not going to tell them what pressure they're at. So that can they, one, there's no bias on that, right? Because it is subjective to an extent. And then they're going to compare their fatigue levels between this run and the next run they do, which will be different pressure in the next run type thing.
I had an interview one time with Johnny Kim, and he was
Okay.
telling me that a senior astronaut, I think it was Chris, told him, don't fight the suit.
You'll lose.
Well,
You
what
will lose.
does that mean?
So the suit is designed with joints and with bearings. And so if there's a joint there and it's sized perfectly, it's going to be just a little bit of friction. It's going to bend what? If you're fighting, like if you want to reach out, okay, don't do that in the suit.
Why?
Because there's a bearing here. So you want to roll your shoulder. Then you want to extend this because there's a joint here.
Oh.
And then you want to come over because there's one here. and then you didn't fight the suit. If I do this, I'm having to force all these things over by going this way, and it's got to force it to roll it over.
Oh, so you literally find the path of least resistance.
Yep. If you understand how the suit's designed and where it's designed to move and where it's not, you move that way. And then you're not fighting the suit, and your fatigue level drops way off.
All right, it's time to talk about the sponsor of this video. I've got two things to tell you right off the bat. So number one, this room is never this clean. I'm not gonna pretend like this is the way it is. Number two, I am concerned about making this sponsorship spot too long because I love this product. Today, this video is sponsored by 8 Sleep. This is a product that I fell in love with on my own before they reached out to sponsor Smarter Every Day. My wife likes to sleep cold. I like to sleep more warm. And so I arrived at 8 Sleep and decided to invest in this technology. So you remember how earlier in the episode I explained that there's this undergarment that astronauts wear to keep their bodies cool inside the spacesuit? Well, that's exactly what this is, but for your bed. Well, it's not exactly what it is, but it's the same technology. You have these cooling tubes and liquid runs inside, and that liquid will keep your body at whatever temperature is ideal for sleep. So there's two elements to the 8 Sleep pod. The cover that goes over your mattress and has the cooling and heating channels in it. And then there's the hub, which sits to the side of your bed that contains the water and does the heating and cooling. The whole thing is controlled by an app on your phone that provides all sorts of really useful feedback on the quality of your sleep. The fact that I get a sleep score every day, it's made me mindful about my rest. This has sensors in it to get your heart rate, your temperature. It can measure when you're in deep sleep, light sleep, REM. It's incredible. And I like looking at all those metrics and imagining like what is causing my heart rate to fall later than normal. Is it caffeine? Is it because I was exercising? What is it? Just for fun, here's a FLIR image. You can see my wife's side of the bed is colder than mine. 8sleep.com/smarter. Get you $200 off the pod. When 8 Sleep agreed to sponsor Smarter Every Day, I said, will you please send me one cut in half so I can look at it because I'm a nerd? They said yes, and check this out. Okay, it's different than I thought. It's not like tubes. They must have a large stamp that they can heat weld it together. And look, they make this grid right here. There's a seam down the middle for one side of the bed versus the other. But look at this. So it's like a mesh. You see that? All the water runs through there, and they have the sensors integrated here. This is the controller. I would love to know how that works. There's gotta be a data card in here. The data must go, it's just ribbon cables. No, that's a USB type interface there. So the flow, like the valves must be over here in the hub. That must be how it works. I did a broad market analysis for the Sandlin family, decided to make the plunge. Very happy I did. My wife loves it. I love it. 8sleep.com/smarter, $200 off the pod. Even if now is not the time for you to make the investment, at least check it out, see what you think. That would be great. So anyway, that's it. Let's go back and check out the spacesuits and see how these things work. Okay, so we're talking about teaching modern astronauts how to walk across the surface of the moon. And when you first think about it, you think, well, the Earth is 1G and the moon is 1/6 G, therefore it must be easier to walk on the surface of the moon, at least from an exertion standpoint. Now, it seems on the surface that it would be that way, but it's actually quite complicated. Think about it. So your weight, yes, is 1/6 as much, but your mass is the same, which means the inertia is the same. A while back, I talked about how to land on the surface of the moon, and I really like the illustration that we use. Like we compared it to a helicopter. I like the animation, and it explains this problem in a very interesting way. So let's go back and watch that. If you think about a helicopter, it has to offset its own weight, right? So if you've got the weight here, then you have lift that's pulling it up at a certain amount to offset that, right? If you decide to translate forward, meaning you want to tilt the helicopter forward and you want to move in that direction, you still have a vertical component of lift that's going to offset that weight, but you also have this horizontal component that will let you accelerate forward. Now that makes sense on Earth, but the problem is if you're in a spacecraft and your spacecraft has 1/6 the weight of a helicopter, even if they're the same mass, you have to go with me here. Think about it. If you have a very small thrust required to lift that thing, if you tilt it over and try to translate in the same acceleration moving forward, it's not going to work because as you tilt that thing forward, the horizontal component of your acceleration is far lower because you're not thrusting as much. So in order to get the same acceleration in the horizontal direction, you would have to tilt the spacecraft over much farther than you would a helicopter. This is the problem they had to figure out how to solve.
They considered a helicopter and a lunar vehicle of the same mass. Over Earth in the helicopter, and if there were no drag, the horizontal component of acceleration would be approximately proportional to the tilt angle of the rotor. Over the moon, where there is definitely no drag, and weight is only 1/6 of Earth, the same amount of acceleration requires nearly 6 times the tilt angle.
That Neil Armstrong, pretty smart guy. So just like flying on the moon is different, walking on the moon is different. And it has to do with the fact that your inertia is the same, the amount of force it takes to move that mass is the same, but the weight is different. It's a fascinating problem. So think about it. If you're walking on the surface of the moon, like right now, if my CG is right here, the center of gravity of my whole body here, I just have to keep that up, and when I walk, I lean forward just a little bit. On the moon, you have to translate that force into the ground, and you might have to lean a different amount. If I have to move my CG more in order to tilt forward and walk, I put my CG out over my feet. And so I have to catch up to it. So a lot of the falls that you'll see of the Apollo astronauts, it's mismanagement of the CG. They're bumbling around trying to get their feet under the CG. It's fascinating once you think about the physics of what's involved here. Another way to explain this phenomenon is a quote by Arthur C. Clarke in 2001, A Space Odyssey. He said that you are 6 times more sluggish than your weight would suggest, which is interesting because it means, like, if I'm walking straight, I'm okay, but the moment I have to change directions, my inertia wants to keep going forward. So knowing that, watch a couple of the Apollo astronauts walk around and see the moment that they mismanage their CG and it gets out over their feet. So this is a thing that the astronauts need to train for here on Earth before they go.
Right, they say give it a slight rotation clockwise as you're lifting out.
Okay.
EVA flight.
Hey there. Yeah, sure not. I mean, material is not white. It's just the same as it, rat. Here we go again. Give me a help.
Flight science.
Go ahead.
We just don't have.
Did you see? It's amazing, isn't it? Once you start seeing the complicating factors, it's like, wow, this is just physics. Now, there's another physics thing that we have to consider because we're in the neutral buoyancy lab. So on the moon, there's no drag. In the neutral buoyancy lab, there is drag. So the rate at which you fall would be different. That's one thing. But if we're going to have this simulate the fact that we are in 1/6 the weight, we have to figure out how to float 5/6 of our weight away, right? And that's exactly what they do in the neutral buoyancy lab. But you have to do that in a very special way that I didn't understand, and Dom does a great job of explaining how they do this.
So your suit's 4 psid delta, so it's essentially inflated. It's going to be buoyant. I need to make sure that your center of mass is where it's going to be predicted for your flight unit. But I also have to co-locate that with your center of buoyancy, because otherwise you'll be too stable all the time, or even though I'm 1/6 G weight, but now it's giving me a righting moment. So these need to be together. So my trick is to locate those two together. I know where they should be.
So that the center of buoyancy isn't a thing.
Right, correct.
Because if they're at the same
It's
location, it's like it's not even
I
the
have
thing.
no orientation, no preferred orientation, just like 0G. It's not going to roll, it's not going to flip, it's not going to whatever.
Is that what you're about to show me here?
Yep. And so how do we figure that out? How do we actually measure that in a suit? So aircraft, when we weigh and balance those, we put them on 3 jack stands. And there's a load cell in each one, and it will give me a resultant axis. And then I tilt it 20 degrees, and I get a second axis, and where they cross is my center of mass. Now I got to do that with you in a spacesuit.
Okay.
So here are my 3 jack stands and my load cells. And
This is a load cell.
there's a load cell right here.
Okay.
Okay, and so I'm on 3 points, and I'm going to stand in here and lock my suit in up here and hold on to those handles up there, so I know exactly where I'm. And you'll be able to see this tomorrow. It'll be.
Is this like a seesaw?
Yep, because this whole thing will rotate 20 degrees. This whole thing will rotate. I'm not going to rotate it now.
Okay.
But I'll unpin it, and you'll see this whole thing will rotate that person in that spacesuit that day 20 degrees, and I'll get a resultant. And there's going to be there's a little dive display underwater, and it's going to show the diver where that is, and he's going to move, or she is going to move the weights around until those line up.
It just clicked. So what Dom just said blew my mind, and in order to understand it, I kind of need to work it backwards. So let's pretend we have an astronaut here, and we have the center of gravity of that astronaut right here. So that would create an imaginary gravity vector going straight down. You see that? That's the weight of the astronaut. If you were to tilt this astronaut forward, the gravity vector would still be pointing down. Do you see that? Now here's the interesting thing. If you were to just go back like this, you can see that those 2 points intersect each other. Now let's think about this backwards. Let's say that we have this scale set up that Dom tells us about. We've got some scale parts there in front of the astronaut, some behind. In fact, let's just have the top view of the astronaut here so you can see it like this. So we've got one scale thing there, we've got one back here, and we've got one here. If we were to place the astronaut in there and weigh things on this scale, let's say, for example, we have some weight here on this one right here, and we measure some other weight here. Now the same happens back here. If you were to average out the force of those 3 points, you would get the center of gravity. So you basically take the position times the weight, and then you average it all, and then you end up with the center of gravity. The same works here. But if you look at it, if we have more weight on this side, that's going to make the center of gravity move this way. If we were to reverse it, and we were to put more weight over here, then over here, then that center of gravity is going to shift forward. Do you see that? So what's actually happening on the astronaut, because you've got the pliss on the back, the big backpack, is you've got more weight in the back, which means the center of gravity is back here to the back. Now the interesting thing about using load cells like this is you can only get one position for the center of gravity. You're not getting a 3D position like this, you're only getting a line straight up and down. You see that? So the center of gravity is somewhere along that line because it's kind of like a seesaw, right? Now when we tilt this thing forward, the same thing happens. And so we can do that again, and then we can, just like we did before, where those 2 lines intersect, we now know what the center of gravity of the astronaut is, which is fascinating. Now, when we take this thing and we put it down in the pool, we come up with another position, and this is called the CB, the center of buoyancy. The interesting thing about the center of buoyancy is that it might not be where you want. It might be off and up like that, and if that's the case, you have a problem because you have offset forces. So to explain this instability, I have another view of an astronaut from the front on here, and you can see the CG of the astronaut is right here in the middle, right? Let's say that they get down there and they start weighing everything out. The CG is the weight of the astronaut there, so you've got a force down, and then the center of buoyancy after getting on the tilty scale underwater is calculated to be like right here. And the goal of that, of course, is to offset 5/6 of the weight of the astronaut. Now let's say they're not lined up. The center of buoyancy is too far to the right of the CG. Now if you look at it, that's going to create this floaty force up there, and it's going to create a torque. And if you think about that, you can kind of see how that would happen. And so the astronaut's leg over here would be doing more work than over here, and it would not be a good run. This would not be good data for a lunar run. So what you want is the divers to trim out the astronaut such that the center of buoyancy is at least aligned with the CG, right? Because then there's still a problem, right? Because now the top of the astronaut is going to be pulling up, and so it's going to be easier to stand, right? Well, if the center of buoyancy is too far below, then your legs are going to want to flip over your head. So what do you do in order to get that center of buoyancy right on top of the center of gravity? Now the divers and the team running the test are pretty clever about this. They have all these weights in these conformal pockets around the astronaut, and what they can do is, if they notice that the CG and the CB are not quite where they're supposed to be, what they can do is they can start moving these weights. They can say, oh, I need to take some from this pocket over here, and as long as it still equals out to 1/6 the weight, that'll move the CG, and they can do things all over the astronaut. You could even add foam blocks to make it float in certain places so you can change the center of buoyancy until the CG and the CB are right on top of each other, and the astronaut has a stable lunar run. It's like they're walking on the surface of the moon. I never would have thought about this. And the fact that you can use this tilty astronaut mechanism to determine the CG and the CB if you do it underwater, I think that's really clever. Now, you can't directly measure the CB. You have to infer that from the data. That's a little more complicated, but it's fascinating. I never thought that you'd have to calculate the 3-dimensional position of the center of gravity and the center of buoyancy, and that would help you emulate a lunar run at the bottom of a swimming pool. It's amazing. What do you call this when you put them on the scale? I'm going to call it the scale.
Okay, we call this our partial gravity weighout system. So this will be on the bottom of the pool tomorrow when you dive.
Really?
And you'll be able to see what's going on that way. but we'll take them down, we'll trim them out to make sure we know where that center of buoyancy is. Then we'll swim them over to here, plug them in, put the extra weights on, make sure they line up, they're in the correct spot. Now go do your testing.
It's unclear where we are, but we're like, the pool is there. That's where I did the put your mask on first thing back in the day. There's a big crane up there, and so I'm assuming you're going to pick this thing up with a crane and put it in?
Correct, and we only need it for the lunar runs. That's why it's out here, and we don't leave it underwater. So, but it will be in before you show up tomorrow. So I wanted you to be able to see it today.
So what Dom just showed us is extremely important, and we'll revisit that later, but we know we're at the NBL to run a test on spacesuits. So let's go learn about the specific test we're running today. All right, so now we're with Adam. Adam, you're a test director, right? Tester conductor, or what do you say?
Test conductor, yes.
Okay, engineer type?
I am an engineer, yes, by training, but I'm in the operations team at NASA now.
So you're going to be running the test tomorrow that I'm going to be observing.
That's correct.
Okay, and how long have you been planning this?
About 2.5 months.
Really?
Yeah.
Just doing the paperwork for this one test?
Yes, and actually that is a very quick turnaround. But yeah, now we're executing the test, and it's very exciting.
So I'm a test engineer by training.
Yes.
So what are your objectives? What are you trying to figure out?
Okay, this test is about characterizing EVA performance at an elevated suit pressure. On the space station right now, the EMU spacesuit operates at 4.3 psi. We want to see what this spacesuit, what it would look like to operate at 6.2 psi, or even higher pressures. But right now we're focused on this 6.2 number.
Okay, so I'm a newbie to all this.
Yeah.
But I'm assuming, it sounds to me like if you operate at 6.2?
6.2.
If you operate at 6.2 psi, that sounds like more oxygen, which sounds like a waste of resources. So there must be a reason why you want to do that, because it sounds like the suit's going to be inflated more, it's going to be harder to operate, and you're going to use more oxygen. So why would you want to do this?
Yeah, that's a great question, and it all has to do with pre-breathe time. And so that's the amount of time it takes you to get from the pressure that you're at in your space habitat or your vehicle to the pressure that you're going to be at in your space suit. And so using the ISS as an example, the ISS is at 14.7 psi, similar to us here on Earth, and the spacesuit is at 4.3 psi. Just like scuba divers have to deal with decompression sickness going from a higher pressure to a lower pressure, it's the same thing with astronauts. And so getting to 4.3 psi takes time, like literally 3.5 hours.
They're suited up. So they're in the suit for 3 or 4 hours?
They are.
Or just in an airlock?
Yeah, part of it they are breathing 100% oxygen, not in the suit. Part of it they depress the entire volume of the Quest airlock and the crew lock, still not in the suit to 10.2 psi, and then they get in the suit and they do about an hour of what's called in-suit light exercise. So they alternate between like 15 minutes of rest and 15 minutes of light exercise, like moving their arms and legs. So yes, like that entire process before they start to depressurize the airlock to even start their EVA is almost 3.5 hours long.
Okay, I didn't realize that. So question, why? I'm assuming it has something to do with oxygen or nitrogen in the blood and the bends, but like physiologically, why do they have to do that?
Yeah, that's exactly right. It's as you go to higher pressures, the nitrogen is dissolved into your bloodstream at that pressure. And so if you decrease the pressure too fast, then those nitrogen bubbles, they can bubble and create these, the bends, and just keeping it simple. There's a lot of bad things that can happen.
So because they're going to a lower pressure, you could get the bends just walking out of the airlock, or just starting your EVA. So you have to first get it's like decompressing when you're going up in altitude, so to speak, in a scuba situation.
Exactly.
Same thing.
It's all about the speed at which you decompress. And so in scuba diving, you go down, depending on how long you stay at the bottom, tells you how long it should take you to get to the top.
So by doing, a higher pressure run in the suit, there's trade-offs. So it's good because you don't have to pre-breathe as much, I assume?
That's the goal. We're trying to reduce the amount of time.
Do we know the amount of time it would take? Have we done the math?
Well, so it all depends on what atmosphere your vehicle is designed for. And so really it's that distance. It's the distance between what your vehicle's at and what your suit is at. And so you can reduce the pressure of your vehicle that the astronauts live at and keep the suit pressure the same, about 4.3, and that lowers the gap and reduces the pre-breathe time. Another way to do it is increase the the pressure of your suit, which also brings those closer together. And so in an ideal world, the pressure of the suit would equal the pressure of your space vehicle, and that would be the zero pre-breathe scenario, where all you have to do is get in your spacesuit, do all your leak checks and everything, and then you walk out the door.
I think in a science fiction environment, or like when you're reading books and stuff like that, that's what you think happens. I'm just going to put my suit on and go outside. It's not what happens at all.
No, and I don't think people realize it. Like, astronauts go and do spacewalks that are like 6 hours, 7 hours, 8 hours long sometimes, and that in itself is one of the hardest things that they ever do. Not only that, they are doing this pre-breathe stuff for like 3.5 hours before that. So they're in the suit for a very long time. So we want to minimize that pre-breathe portion so that we can maximize their time doing a spacewalk in the spacesuit and getting our science objectives or whatever objectives completed.
Okay, so I'm assuming the suit was designed for a certain pressure. Like, what suit are we going to be doing the test in?
So this will be what's called the XEMU. This is the NASA Government Reference Design suit that they've been working on for the last few years. And so it's actually been designed with this in mind. So its pressure rate was rated to operate, I think, up to 8.2 or 8 psi, somewhere around there. And so this is all within normal bounds because we knew this was going to be something we were going to want to look at.
This is like a pathfinding type test. You'll get the data, you'll apply it moving forward, and then you'll know what to do in space.
Correct.
How do we know what the chamber pressure isn't the term? You can tell I'm a mechanical engineer. Do we know what the habitat pressure is going to be on HLS?
Yes, we do know that, and I'm not sure how much I can speak on that topic directly.
But it is a known thing.
It is a known thing, and it's one of the knobs that we can turn. So
we know where we're going to be, and we know what we're going to run the suit at, and that tells us what our pre-breathe time is going to be.
That's right, yes. The program management folks are looking at all the different knobs, and we're just trying to understand how do we minimize the pre-breathe time, because this really has to do with our timeline when we're on the surface of the moon. In these early missions, we'll be on the surface for 6 days. We want to do 4 8-hour EVAs if possible, right?
Yeah.
And so if we have to spend an hour and a half, 2 hours, 3 hours doing pre-breathe, like that's wasted time. So
it's a long day.
Yeah, so that's kind of what all this effort is. And there's trades with all of these decisions, right, regarding the atmosphere and stuff. So it's a complex decision to make.
Will they start the run at 4 psi and then go to 6, or will this be a high pressure run the whole time?
So that's actually something that's really interesting about this test, is the subjects will be blinded to the pressure they're operating at.
Really?
Yes. I am blinded, and the rest of the test team is blinded. So only a few people as part of our test leadership, and obviously the people here at the NBL that like turn the dials and stuff know what the pressure is, but the astronauts will not know. We have the ability to run each of them at a different pressure. So one person may be at a higher pressure, one person may be at a lower pressure. We don't know what decisions were made by the leadership.
The next morning, I showed up, and the first order of business was to fill out some paperwork and do a pre-dive medical check where they just confirmed from a health standpoint that I was safe to dive.
Remember the hypoxia video? She saved my life. Yeah.
Pat took me poolside and introduced me to the person in the red shirt, who today was Mike Caldhill. Whoever's wearing a red shirt is in charge of the whole pool, and you don't wear a red shirt unless unless you're that designated person. We checked out the equipment and, well, mainly my ability to work the equipment, and then I headed upstairs to catch a bit of the pre-dive meeting where the various departments involved were going over the specifics for the day. The two astronauts who'd be doing the dive are Jessica Meir and Randy Bresnick. Both are seasoned astronauts with a combined time of over a year in space. These are seasoned spacewalk experts. You can see through all this footage that they have a lot of time in microgravity and they know what they're doing. This, however, will be their first dive training with these new suits in this lunar environment. I headed down to the pool deck as the operations began.
Okay, so we're poolside now. I see the thing in the pool.
Yeah.
It's, what's it called again?
So this is our partial gravity way out stand.
Yeah.
And that's going to go all the way to the bottom. Right now we're just trying to get the temperature to equalize, because those load cells are, the accuracy and precision, if your thermal's off a little bit. So the 86-degree water is not the same as the air. So we put it in, we're doing a little warm soak right now. That'll go all the way to the bottom, and then by the time the crew gets in, they'll be able to walk right on, do their way out. The divers will adjust that. They'll have a good 1/6, and they'll be good to go for their run.
So here's the way out stand, and I'm seeing rocks over there. And I'm sorry, how is this working?
Okay, so this semicircular here is a representative of the human landing system,
Okay.
the lander. And so there's an airlock that's straight down under here,
Okay.
mock-up. So they'll walk out of that airlock, they'll go into this little front porch area, which is actually representative of the elevator that would take them down to the surface. Because
this would be the elevator that descends to the surface?
The rectangular part out there.
Got it, okay.
Right, and then they'll walk off that ramp. Normally it'd be about a 30-foot lower, but there's no reason to 30-foot lower. We'll just, walk out here, they do that, they close up, they get used to that, they open the door, I've lowered to the bottom, I walk out and I start my EVA on the surface. And so, the rocks are there, so when we have our lighting intensity, it throws those shadows, gives them the area, and it gives them an area to work in.
So these models in the Neutral Buoyancy Lab are what's called low fidelity mock-ups. They're mostly made out of materials that won't corrode, like stainless steel and plastic, but they also can't trap air. That's why you see the grating down there. And so when I looked at this ring, I was like, it's a ring. It's a psychological representation of the diameter of that rocket. And then I was like, wait a second, that's a big rocket. And then I got excited. I started thinking about all the engineers designing things to go in there and like what it was going to look like in the end. And so I got excited about it. But at the same time, right now, it's just like, this is a 3D space that we can use. It's like a little playground. And so I thought that was really interesting. And it took my mind to weird places, realizing that this is a lot bigger than what Neil and Buzz went to the moon in. And so this is the first moment that I got really excited.
So I'm thinking about the gloves because that's going to be affected by the pressure. And they're putting the gloves on now. Randy's requesting a certain tension in the gloves. So that's going to be affected by the pressure inside the suit.
So there's actually a bar across the palm, right where it folds there.
Yeah.
And that's what they were tightening and cinching up in the back. So it pulls that part in.
So it's not just a balloon coming out from the palm. Yeah.
So after they finish getting the astronauts in their suits, they hoist them on a platform and lower them down into the pool.
TDECS system alarms are enabled. Verified no alarms present that will impact testing.
Copy that, no alarms. Good morning, safety divers. This is Greg, your test director. How do you read me this morning? Copy on 1, copy 2. Let me check this back up. Alright, safety divers, I'm on back up. How do you read me? EV1 safety, EV2 safety. Copy that. EV1, EV2. How do you read me on back up?
EV1 loud and clear.
2 loud and clear.
Loud and clear on back up. Alright, safety divers, purge all air trapped by the delta pressure valve adjustment knob, please. Give me an OK sound when complete. Copy on 2, safety divers, thank you. And copy on 1, safety divers, thank you.
So at this point, we have astronauts in the pool, which is awesome. They have like 6 hours of dive time, and I, as an observer, have a little over 2. So I decided I was going to stagger when I got in the pool so I could observe the actual test taking place. So while they were doing their leak checks, I checked in with Adam.
So does this get old?
Does this get old? It does not get old. I'm actually a test conductor in training, so this is my certification run. So this is my 3rd time kind of running the show, so to speak, and it is just so much fun. I mean, look at this. Like this is the premier underwater training facility in the world for astronauts, and I get to be the person that talks to the astronauts and help to work through the test team. And you can just see how many people it takes to do this. Not only to pull it off in general, but just to pull it off safely. And so it's just it's a dream come true to be here. It's a lot of fun.
So at the end of the day, you'll be certified, hopefully.
At the end of the day, hopefully I will be certified. I have somebody evaluating me, and hopefully I'll get that.
Oh, who is that?
Up.
I gotta know who is that? Who's?
Her name is Tess. She's up there sitting in my seat right now, covering the room. So.
Oh, I gotta talk to Tess.
Yeah, she'll be my partner in crime.
Okay.
And my evaluator.
Okay, great. All right, we'll see how you do, Adam.
Yes, thank you.
We're going to be judging you from now on.
That's all right, Doc. If you can't handle pressure well, this isn't the job for you, right? There's a lot of people. It's very dynamic, but I love the pressure. It's kind of like being a flight controller.
Okay.
Just a different flavor of it.
That's cool.
As Randy and Jessica made their way to the bottom of the pool to begin the trimming and weighing out of the spacesuits, I was able to catch up with one of the suit engineers as she waited. What was your name?
So my name is Christine Davis, and I'm an advanced suit engineer for the advanced suit team here at NASA.
So I saw Joel over here working with Randy, and you were working with Jessica to get her suited up.
Yes.
So what's your background?
I went to Kansas State University to get a mechanical engineering degree. And
that is the correct type of engineering, yeah.
And then I started full-time in 2016, and I've been working on the team since then.
Okay. So what were you doing with Jessica getting her ready?
So I was getting her ready because I'm her suit test engineer. So I'm helping through all the procedures of getting her suited up. So that's suit donning, making sure that her cooling garment's connected, there's no leaks, getting her comfortably in the suit, making sure that all of our straps are tight. So we have boot tightening straps to make sure her boots have good fit, same with her gloves, making sure she can reach her Valsalva and her drink bag, and making sure that then when she gets pressurized that we stay safe through that pressurization.
Now the Valsalva, my understanding, like when I'm about to dive here, and when I go down I hold my nose to clear my ears.
Yep, and you can't do that in the suit.
So what do you do?
So you use that Valsalva device. So it's basically a foam block that the crew members can use to block their nostrils, similar to like when you squeeze your nose when you're diving, and it helps just for you to clear your ears. And some people don't need to use it, they can just swallow or move their jaw, but sometimes you need that extra little bit of oomph to get the Valsalva, so they use that device.
Oh, that's awesome. So how long have you been doing this?
So I've been doing this for 8 years full-time since in March.
Do you love it?
I love it.
Yeah?
So much fun, yeah.
And you like working with the astronauts?
Yeah, so much fun. It's always a great day when we get to do testing.
It's on the bottom.
Copy that. EV2's on the bottom. All right, we're going to go ahead and do a final comm check. I'll turn it over to Mr. Peterman, our comm technician.
So are you dedicated to Jessica's suit, or you work for all the different?
So I work on the XEMU specifically. I'm one of our suit test engineers, so I help run some of our suit tests. I also am supporting the XEVAS contract. So XEVAS is the exploration suits that we're going to be working with Axiom and Collins, 2 suit vendors on. So I'm helping on the Insight team, so from the government, kind of reviewing their documents, reviewing their suit design, making sure that suit's being developed safely. So that way when we transition from the XEMU government reference to their suits for flight, we're ready to go.
You're wicked smart. It's so good talking to a fellow mechanical engineer. That's great. Yeah, well, this is fantastic. Thank you so much.
Down on the bottom, the divers trimmed out the astronauts to first make them completely neutrally buoyant. They tipped them over and spun them around and adjusted weights and foam to various positions until no matter what orientation they placed them in, they would float completely still. Once they had obtained neutral buoyancy, they then had them stand on the bottom and added more weights evenly to create the 1/6 gravity pushing down on them. After that, they walk over to the partial gravity weighout system and take an upright measurement that gives them a vertical vector of the location of the center of gravity between the 3 load cells. Then the divers tip them forward 20 degrees, which gives them another vector, and the intersection of those 2 vectors is where the center of gravity is in 3-dimensional space.
EV1 safety divers, if you can stand clear from the PGWS stand. EV1, if you can place your hand on the handhold and remain still while we take measurement.
The team topside analyzes this information and compares it to computer models of where they want the center of gravity and center of buoyancy to be. In this case, Jessica's suit requires an adjustment because the data revealed she has a riding moment.
Safety divers for EV2, let me get you to take a 2-pound snake weight off of each leg.
And Jessica, just some additional words here. So looking at the numbers, your CB and CG measurement is just a little bit further away than we've seen in previous runs. So the team is just going to remove these 2 leg weights to try to better align your CB and CG and also get you closer to the 1/6 mark.
All right, here we go. Got the suit on.
Yep, we're good to go.
Yep.
Okay, it was time to do the dive. I was very excited. Even though they keep the pool at a balmy 86 degrees, I decided to wear a shorty because if you're in the water for several hours, you could get cold still. So we got everything suited up, made sure the equipment worked, and then Pat led the way. Once we first descended into the water, it's like an entirely new world opened up. It was surreal to swim over a life-size model of the International Space Station. My favorite thing was the Canadarm was right there. It's a mock-up that they use, only it doesn't use electrical actuators. It uses an oil pump to move Canadarm. It was amazing. I kind of got my bearings, and then we went all the way down 40 feet deep to the bottom of the pool. As we approached the bottom, Pat gave me very clear instructions on where I could go and where I couldn't. And I wanted to be a good little diver, and I wanted to obey everything that Pat said. So I made sure that I asked for permission every time I did anything. As I approached the bottom of the pool, I realized that all the attention was on the 2 suited individuals before me. And even the individuals themselves, they were focused on the task at hand, wringing the truth out of these suits. And it was at this moment that I realized I was jealous. I wanted to know which of these suits was at a higher pressure, and I was jealous of the technicians that turned the knobs that knew the answer to that. But for now, it was as simple as picking up rocks to test mobility. At some point, Pat told me that I could explore if I wanted to, and I certainly did. So I swam up to some of the ISS modules, and I got to poke my head up into one of the nodes and look around, and I could see how difficult it would be to manipulate the latches and locks if I had big gloves on. I'm pretty familiar with the International Space Station. I've been in mock-ups before, so I have a 3D model in my head, but floating in the International Space Station was a completely different thing. Like the fact that I was in a 3D interaction with it instead of walking through it like a hall, it felt different. And it instantly made me understand why the neutral buoyancy lab was so important. While I was exploring, I found some of the weights they used to trim out the astronauts, and I was surprised by how heavy they were. After exploring a little bit, Pat took me down to the lunar simulation area of the NBL, which was awesome because there were little bitty Easter eggs that the engineers designed in. You remember when Alan Shepard hit the golf ball, Apollo 14? Where did the ball go? I'll tell you where it went. Right here. The engineers put it into the rock. I thought that was awesome. Also, Pat took me down to the bottom of the pool, and I was surprised to see the footprint of that real smart gentleman that we heard from earlier explaining 1/6G to us. Neil Armstrong's boot print. Okay, to begin the lunar run, I'm going to show you what the astronauts would see. They would begin inside HLS in an airlock, and then they would go out into a larger room before going out onto what will be the elevator, but in this case it's just a ramp. Then they'll go out onto the lunar surface and start exploring. So of course I wanted to position myself just outside of HLS so I could see them coming off the elevator, and that's just what I did.
so much. And divers, do you ever go to lower the ramp?
Once the astronauts came out and started exploring the lunar surface, I was surprised to find that Mission Control was kind of micromanaging them a little bit. They would say, go get this specific shovel from the cart. Now, go retrieve this, put this marker down. I would expect them to say, hey, you're on the moon, go explore. But it was different than I expected, which makes me realize the test conductor, Adam in this case, was probably trying to control all the variables so they could compare the runs between all the different astronauts. At least that's my assumption. For example, there was a pegboard-like structure with the hose that they had to detach and reattach. I'm assuming every astronaut had to manipulate these to test their ability to use their gloves.
Size that represents the sample that you imaginarily took.
One of the signs of a good scuba diver is the ability to control your buoyancy so that you can stay in one spot. I was having to kick and fin all over the place to keep myself where I wanted to be, whereas these divers clearly had a command of their whole body and the area around them. They didn't have to do anything. They could just float where they wanted to be. This told me that they knew exactly what they were doing. The different tasks that the different divers had started to become more clear to me. Some people were just trying to keep the umbilical out of the way of the astronauts. Others were safety observation. They were making sure that the astronauts were safe at all times. The camera operators were making sure that the test conductors could see exactly what was happening in the pool. It was like a beautiful choreographed dance, all happening in 3 dimensions, and people were controlling their own buoyancy, and I was just trying to stay out of the way. Pat was so much better at swimming around than I was. So at one point I gave him the camera and I said, Pat, I want a shot of the wheels on that cart. I want to see how they're interacting with the lunar regolith. Can you go get that shot for me? And of course, he did. Look at how much the astronaut is having to lean over to push the cart. This goes back to that 1/6 G we were talking about. They're not actually getting a lot of purchase in the soil because they don't weigh as much. So they're having to lean really, really hard, and traction's an issue. Think back to that quote earlier, you're 6 times more sluggish than your weight would suggest. You can see it happening right here. The most incredible thing I saw happen right in front of my face. Randy was working on his knees, and the transition off of his knees created a fall. And why he fell is something that you're going to recognize. Let's watch the whole thing play out first, and then we'll go back and replay it, and we'll talk about it.
Sounds like a plan. The last thing you'll need is the tongs, and so you'll walk back to the cart to grab that, and then you can collect your sample.
Did you see what happened? Watch it again and let's talk about it. So Randy kind of mismanages his CG just a little bit because he's too close to the ground, and then it starts to take him over. Now, anyway, when Randy falls, watch what the diver does. She comes over and she says, "Are you okay?" And then Randy apparently tells her yes, and you have another diver getting the umbilical out of the way, and then she makes Randy struggle through on his own. He has to figure it out, and he does. He figures out how to get back up, and they celebrate this together, and all the while everybody's taking the data. And I thought that was amazing. It was so cool to see this at the bottom of the pool. I was feet away from this when it was happening, and I'm excited to share this with you because we're getting to see an astronaut learn how to walk on the moon. Randy's having to figure out how to manage his CG, and that's important for walking on the lunar surface. And that's all gonna factor in to make Artemis successful. Right as they started testing the suits walking up a grade, the dive supervisor announced that my time was up.
You have 5 minutes left. Start making your way to the surface.
I wanted to stay on the moon, but obviously it was time to go. As I swam back up, I was thinking to myself, what an amazing opportunity. I was so thankful to be able to do this. And when I got to the top, I thanked Pat for such an amazing dive and for watching over me and keeping me safe. After I was cleared from the test supervisor, I hit the showers, washed off, and I went up to the control room in time to hear Adam doing some of the qualitative assessments with the astronauts.
First up is perceived exertion. So this is that 0 to 10 scale.
I said give it a 4.
Give me 1 second.
Thanks again, you all did awesome, and looking forward to talking more about it when you're out of the suits.
Sounds good.
That's good, thank you. It was a lot of fun. Sorry, I guess this is way more fun.
So this was Adam doing his checkout, right?
Yes.
And you were observing Adam as Adam
I'm
was
about to be put on the spot, I think. That's what's about to happen.
So how did he do?
He did great.
Did he?
You know, Adam's a really strong TC. I think we all kind of knew going in that he was going to kick butt.
Yeah?
And he did not disappoint in any way.
Really?
It's fun with these guys because they've been astronauts for quite some time.
Right.
And so they've gone through the basics of learning how to do EVA for ISS. So they learned how to move in that suit. They learned how to do those tasks. And this is almost resetting them back to EVA 101 with a new suit and new tasks. And so they understand the mindset for learning these things, which is you can fail and it's okay.
So let's go see what the astronauts thought about the run. Let's start by talking to Randy.
I noticed that you were having trouble at one point standing up because you had to learn. This is the first time you had to learn that, right?
The way out is what you have to get used to. Where's that center of gravity and how much does it tip you over and you start falling? And so without as much traction on the ground, when you go into the sand, you know, now it's tough to get your leg out there and stabilize yourself or swing it around. And so there's one point where I ended up falling onto my back, and where I was on the hard ground, I was able to get enough traction with the boot to be able to, get me up on a shoulder, and then be able to get over and then stand up. When I was in the ceiling, I felt like I was breakdancing. I was just spinning around until I finally got a purchase and I was able to get the center of gravity up over my arm to be able to get on the front.
So it was interesting watching that because you were problem solving in real time.
Yep.
And it was pretty cool because you get to figure that out here instead of, on the lunar surface. You'll say, oh, well, with this suit, it has mobility in this direction. I can do this, I can't do that. Do you learn things like that?
Oh, absolutely, and that's the whole reason why we have this facility and do our EVA training for 0G in this facility as well, because you figure out that we come in at everything with this 1G orientation. Up is up and down is down. And we can go in here with the space station and train for microgravity in every position as possible. And you have to force yourself to get out of those positions that are heads up to get in the right position for the best one for work, or maybe it's even inverted. And that allows you to then have this whole toolkit, a whole array of attitudes that your brain thinks in. Yeah. And so that was the same thing, exactly what you observed, going, okay, well that didn't work. Okay, that didn't work. All right, let's try this. Okay, let's try this leg back instead of this leg. And so it was trial and error, and then found something that worked.
What do you think about the tools they gave you to work with on the surface?
We're evaluating and evolving tools. We got some improvements, just like we got improvements with the suit, and certainly improvements with the crew members too.
Thank you so much. Thanks for your time. Okay, end of the day here. First of all, how on earth do you do this much stuff in a day and you're still awake? I'm so thankful for everything. How was the run for you?
It was so much fun today. I really had a blast. I learned a lot. Personally, I thought that the run today was going to be very difficult using the XCMU in the pool. I thought, based on the suit fit checks I had and then the pogo, offloaded run that I had, that it was going to be really difficult. And I'm also used to being in the EMU, the spacesuit that we use on the space station. Those runs are super taxing. If it's a difficult, kind of normal run, you're really completely spent at the end, like metabolic equivalent of running a marathon, forearms completely exhausted. You're just ready to get home and lie down. And I feel like I could go do my normal workout right now after that. So it was only a fraction of the effort required. And I think the main reason for that is because you actually can use our bodies as they evolved. You can use your entire body. You're using your big leg muscles to walk around, you're using your core muscles, and you're only using your hands for the types of things, you know, that we would do here on Earth with gravity. In the EMU, you're doing everything with your upper body. So you're moving yourself, translating hand to hand, moving your entire body and the whole mass of the suit with your forearms, then doing all the intricate tools and everything with your forearms. Whereas here you had just more of a normal distribution. So I think that's why it just felt much less tiring.
It felt more natural.
It did feel more natural, which makes sense because we evolved with gravity, and there's 1/6 G on the moon.
Yeah. So you're upright. You actually have an orientation vector.
Right. Absolutely.
Yeah, that's good.
That does make writing yourself and spatial awareness a lot easier.
I noticed you found I'm just going to do it because it's easier. You found a squat that kind of felt good to you.
I did, and that was surprising to me too, based on, you know, some of the earlier stuff. I had a lot more stability than I thought, and I would kneel down. What really worked well for me was I could kneel down like this, and that was fine, but actually I had even more stability if I put a leg out like this.
I saw that.
And so that was kind of my preferred position, and I felt, you know, surprisingly like stable, that I could stay there forever. So
it was interesting. I was in the room when they were talking about you doing that. They're like, she found something that she likes, and it seems to be stable. So thank you so much for your time. I'm grateful. Do you think it was a good test?
It was great. Yeah, hopefully it really will inform, you know, the biggest question of the test today were the different pressures that we're using. We don't know for sure what pressure was used. I felt pretty confident that I did know what it was.
Are you allowed to say?
I don't know. I don't know that it really matters because it's blind for everybody, you know.
Yeah.
I have nothing to compare it to right now, but it felt like the normal pressure to me.
Yeah.
I didn't feel more fatigued in my hands as I anticipated I would in the higher pressure. And I had done one of the earlier glove box tests and did notice a very marked difference in that hand and forearm fatigue and dexterity in the higher pressure. So my hunch today is that it was normal. If this was a higher pressure, then we're in great shape, because if it's this easy at the higher pressure, then we're set.
I noticed Randy was struggling a couple of times more than you. That was my observation from the bottom. But I'm not a smart NASA person, so I don't know.
Well, and interestingly, you know, it could just be that I'm better than Randy. But, you know, just kidding, Randy, just kidding. You know, yeah, he could have been at the higher pressure, and I could have been at the lower pressure. That was one of the permutations, was that we were actually at different pressures. And it's funny, I had to kind of remind myself of that partway through. So I'm like, oh, I wonder, you know, what this is relative to when we're giving kind of different scores. It's a little bit difficult when we're using this subjective scoring criteria. You know, you have a sliding scale, but still every individual interprets things differently. So,
well, thank you so much. First one here this morning, last one to leave. I'm impressed by you. I know it's the first time we met, but it's a pleasure.
Thanks so much, Destin. Great meeting you.
So the big question that we had at the beginning of the episode, what is it? The question is, what is the atmospheric pressure inside the lander for Artemis? That's a big question. Now that we know all this stuff that we learned in this episode, let's talk about it. Right now on the International Space Station, the atmospheric pressure is a little over 100 kilopascals, 14.7 psi. If I want to go out on a spacewalk, an EVA, I have to pre-breathe for 2 hours and then get my suit on and then pre-breathe for another hour and a half. That might make sense on the International Space Station, which is a lab in orbit designed to study the effects of microgravity on things. It would make sense for the only variable to be gravity on Earth, microgravity up there, right? So similar atmospheres. That's not the case on the moon. The mission for the moon is exploring the moon and living there. EVAs are kind of the point. So if we have an environment where we're trying to do EVAs, it seems like we would want to tailor the atmosphere to be more conducive to EVAs, meaning we have a lower pre-breathe time. So the question I have is, well, what did they do on Apollo? Now I know Apollo was flags and footprints. It wasn't like a sustained human presence on the moon, but Apollo, they had atmospheres of around 5 psi in the lander. So they could just put on their suit, depressurize the habitat they were in, and they could go outside without any pre-breathe time. It's called a zero pre-breathe time. That is the goal. You go forward and you start looking at what happened on Skylab. Skylab was a 22-foot diameter spacecraft, which is comparable to the 30-foot diameter HLS we're going to have on Artemis. Skylab had a 5 psi oxygen-rich environment, and that's what they did. And so when they did EVAs, pre-breathing wasn't as big of a deal. Now, that all sounds great, like, oh, well, let's just make everything 5 psi and it's not a problem anymore. Except that an oxygen-rich environment is more of a flame hazard. Apollo engineers spent an incredible amount of time working on this, specifically looking at what materials could be used on board. Here's another issue I hadn't thought about. With off-the-shelf electronics, they use air to get heat away from the chips. If you're at a lower pressure, you can't get enough heat away, so equipment could overheat unless it's designed for that environment. If you oversimplify things all the way, on one end we have pre-breathe time, and on the other end we have fire hazards. That's the most simple you can make this discussion, but there's a whole spectrum of things that need to be chosen. The reason I say this decision is the cornerstone for the future of space exploration is because it's like a standard. Do we have a spacecraft that's a standard pressure? So is Orion going to go to Gateway, it's going to go to HLS, and they're all the same pressure? Probably not. They have different pressures, I'm guessing. So if I was NASA, this is what I would try to do. I would try to design my hardware so that it could be as flexible as possible. That way, if I'm going down to the surface, I'm going to try to maximize the number of EVAs I can do, and I'm going to minimize the number of flammable materials on board. If I'm going forward and I'm going for a longer duration mission, maybe there are physiological effects for humans in a decreased pressure atmosphere for an extended period of time. Maybe it would make sense for a longer duration mission to elevate the pressure. This adaptable architecture would enable you to do tons of things. For example, the Russians, they sometimes start their spacewalks at a higher pressure in the suit. And so when they start the EVA, their suits are rigid, and then they transit to the place where they're going to do the work, and then they decrease the pressure, and that way their gloves are more pliable, and they don't have to pre-breathe this long because they basically did the pre-breathing as they were transiting on the EVA. It's a fascinating strategy that's pretty clever. The Neutral Buoyancy Lab is right in the middle of making all this awesome research happen. There's other ways you can get more data, like zero gravity flights and with suspension 5-6G offset to give you more real-time movements. But the Neutral Buoyancy Lab is an indispensable asset. And as a taxpayer, I'm excited that we have it. And I think it's really, really cool that they're able to do these studies. And all the divers, I was just so impressed by all the personnel. It was amazing. So I love this. I hope you enjoyed this episode. For me, this was a treat. I mean, this was wonderful. Big thanks to everyone at NASA for putting up with me and allowing me to do this. I'm so grateful. Also, I want to say thanks to everybody that supports on Patreon, people that support Smarter every day. I mean, this is not a normal video on the internet. I'm aware of that, and you make it possible. So we did this together, and I'm grateful. I also want to say thank you again to the sponsor of this episode, which is 8 Sleep. You can check that out at 8sleep.com/smarter. I got an 8 Sleep pod before they ever reached out to me, so it's a good product. That's it. I'm Destin. You're getting smarter every day. Have a good one. Bye. So when you get done and your clothes are wet, they've got this little device here. I got my wet underwear. I'll put in there, and it spins it up. I need one of these. Okay, getting smarter every day. That's really cool.